Hello everyone. Today I'd like to tell you about a highly relevant topic in materials science, the structural modification of polymers using carbon nanostructures. Let us consider the physicochemical mechanisms that allow us to solve complex industrial challenges at the molecular level. But to understand the true value of these solutions, we first need to look at the fundamental limitations of modern materials. Plastics and engineering polymers have become the structural backbone of modern civilization. They are indispensable everywhere, from simple household items and water pipes in our homes to high-tech components for automobiles, microelectronics, and spacecraft. However, materials scientists face the same stubborn challenge year after year: how to radically increase the strength of plastics and protect them from heat and UV radiation while making the products lighter and more cost-effective. For a long time, the industry tried to solve this using conventional nano-additives, but scientists kept hitting a wall. Standard microparticles are shaped like long fibers or flat flakes. Inside the molten plastic, they behave like dry twigs or tangled yarn, instantly catching onto each other and clumping together. As a result, the liquid plastic becomes too viscous. It loses its flowability, making it impossible to mold complex or high-precision parts. A breakthrough from fundamental science arrived in the form of onion-like graphene. This carbon nanomaterial opens up completely new frontiers in the molecular engineering of plastics, elevating their performance to a whole new level without sacrificing processability. Onion-like graphene consists of spherical carbon nanoparticles ranging from 30 to 60 nanometers in size. At the molecular level, each particle is made of 40 to 60 concentric, perfectly nested graphene spheres. This sp2 hybridized carbon structure boasts ultra-high chemical purity, over 99.5%, and is entirely free of catalytic metal residues. Its perfectly spherical shape is precisely what solves the viscosity problem. Unlike fibers or flakes that get tangled, these carbon nanospheres cannot catch on to one another. Instead, they act like microscopic ball bearings. They glide easily, distribute evenly throughout the volume, and do not hinder the plastic's flow. Consequently, the molten material remains fluid, flawlessly filling molds of any complexity. They trigger the formation of an ultra-dense internal structure, drastically increasing the material's strength. In the production of water and gas pipes, this allows manufacturers to reduce wall thickness without sacrificing reliability. Furthermore, the tight packing of molecules around the carbon spheres creates a robust internal barrier against gases and liquids, giving containers and chemical tanks exceptional resistance to harsh solvents. In engineering thermoplastics like polyamides, polycarbonate, and heat-resistant polymers subjected to high mechanical loads, the additive completely changes the mechanics of material failure. The spherical particles distribute internal stress evenly and literally block the growth of microcracks. A crack simply cannot propagate straight forward. It is forced to bypass the carbon sphere, branching out and losing its destructive energy. Simultaneously, the multi-layered shell acts as a trap for harmful free radicals, raising the plastic's heat resistance by dozens of degrees. Meanwhile, graphene's natural ability to absorb UV radiation protects components from yellowing and degrading under environmental exposure. For anti-friction polymers like polyacetyl and fluoropolymers operating under constant dry friction, such as plastic gears, bushings, and guides, carbon nanospheres offer a unique self-defense mechanism. Under intense friction, the outer layers of the carbon sphere gradually peel off, creating an ultra-thin, self-healing protective film on the rubbing surfaces. This drops the friction coefficient several times over, allowing mechanisms to operate smoothly for extended periods without any liquid lubricants. Finally, onion-like graphene solves major issues in 3D printing and eco-friendly recycling. In 3D printing, it solves the ultimate challenge of poor interlayer bonding. Thanks to their high thermal conductivity, the nanoparticles within the printing filaments instantly distribute heat across the melt zone. The layers fuse at the molecular level, resulting in a monolithic finished part free of brittle joints. In plastic recycling, this material acts as a reinforcing framework. It binds degraded polymer chains together, restoring the properties of recycled plastic back to the level of virgin raw material. Thus, by utilizing the specific geometry and stable hybridization of these carbon nanospheres, we can predictably alter the macroscopic mechanics of polymers without compromising their processing characteristics. This is by no means a complete list of the areas in which carbon nanostructures find their application in modern high-tech industries. Stay with me. It's going to be very interesting.